So,
okay, thank you for the introduction. Good afternoon. Let's go ahead and talk about tank culture of yellowfin tuna, reflecting on 27 years of broodstock management and sustained year-round spawning for research purpose. The other authors of this work are Dan Margulis, Susanna Cusati, and Vernon Yole. So I'm going to start talking a little bit more about who we are and what we do. The Inter-American Tropical Tuna Commission, or ITTC, is an international organization formed by countries that share the same interest in managing the tuna fisheries in the Eastern Pacific Ocean. And among the different research programs, the Early Life History Group, which we are part of it, is responsible for studying the reproductive biology, eggs, larvae, and juveniles of tunas and tuna-like species to understand the factors that affect pre-recruitment growth and survival, and also try to incorporate that into fishery science, so in stock assessment models or recruitment forecasts, anything that can be used as a baseline for the policy making of the country members. So we are fortunate to have laboratory Ashotinis, you can see here in this beautiful picture. So we can conduct our experimental work in this inland facility. The laboratory Ashotinis was established in 1986 in the Pacific coast of Panama. During the early years of the lab, a lot of different research was conducted with species as black skipjack tuna and sierras and other species. But after funding from a Japanese agency and the ITTC in 1993, we switched the focus of our research for the yellowfin tuna. There was a lot of interest in studying these species in captivity. So the first yellowfin tuna capture and stock at the lab was in 1996, and since then, our main broodstock tank has never been emptied or been without fish. The yellowfin tuna is a species that is broadly distributed in tropical and subtropical waters in the world and is absent only in the Mediterranean Sea. Currently, only the stocks in the Indian Ocean are considered to be going underfishing and overfished, but all the other stocks are considered healthy. And the latest FAO report ranked the yellowfin tuna as the 5th major species in marine capture production. And coupled with the skipjack tuna, that is the 3rd most important species, their landings represent 56% of the tuna landings in the world. So you can see the importance of the yellowfin tuna in this multi-billion-dollar industry that is tuna fisheries every year. Now, going back to the lab, clearly we improve our techniques over the course of these 27 years, but overall we have the same methodology in broodstock management as we did when we started. We collect our broodstock in coastal waters of Ashotinis Bay. Upon arrival at the lab, the fish is tagged, weighted, measured, and undergo prophylactic treatment in quarantine tanks. And after, when they're healthy, we transfer them to these holding tanks, our mid-size tanks of 85 cubic meter recirculation system. They stay there for a couple of months, getting used to captivity conditions, and after we transfer them for our main broodstock tank, Tank 1, which has 1,300 cubic meters, 17 meters diameter, and 6 meter depth. We feed our broodstock with a diet of sardine mackerel and squid. The spawns occur naturally, following fluctuations in the ocean. And we have a very strong data collection program. We have a database with all the information from every fish that was ever captured and became a broodstock. Also, all the information with spawning. We collect water quality parameters twice daily since 1996. And for the analysis that I'm going to show, we use a lot of correlation, regression, comparison of means, parametric and non-parametric statistical analysis when appropriate. So after 27 years, what do our broodstock look like in numbers? So 370 fish were part of the main broodstock population from 1996 up until December 2023. And most of the time, our tank had 12 fish. The sex ratio of our broodstock, which can only be determined at that, overall has maintained 1 male to each female. The most frequently cause of death were wall strikes. So the fish hit the wall during the early hours of the day when they are still adjusting their vision from dark to light conditions. That is followed by starvation and blindness, which is often associated. Sometimes the fish can develop a secondary infection in the eye due to friction with other fish in the spawning or feeding events, and that will impair their ability to feed. Also, we have some mortality related with transfers and other causes. The average time our tank spent in tank 1 was 1.3 years, but we had fish living up to 5.2 years in tank 1 with an estimated age at that of 6.8 years. This is very interesting considering that the lifespan of the yellowfin tuna in the wild is considered to be 7 years. So this means that this fish spent most of its life in captivity. There were no differences among females and males in time in tank 1 or age at that, but we can see in the histograms that most of the fish that live longer than 3 years in tank 1 or that had more than 4.2 years at that were females, which is also different from a common theory that the stock assessment of yellowfin tuna has, which defends that the females have a shorter lifespan than males. We don't see this happening with our broodstock. So feeding and FCR. During these 27 years, the average FCR that we had was 20 kilos of fresh feed to convert to kilo of biomass. This is fresh feed, so considering the water weight, it's high, but is still within the same FCR ranges reported for other tuna species as Atlantic bluefin tuna and Pacific bluefin tuna. But clearly, this is one of the biggest hurdles that the industry will have to overcome to reach economic feasibility and environmental sustainability in any tuna project that will be developed. So now the growth of our broodstock, we have length and weight related with the age of the fish of females and males, and we compare that to growth curves from the fish in the wild and in captivity. There were no differences in growth rates among females and males, and the average growth rate of our broodstock in weight was 19 kilos per year, and this is very rapid, considering that the females reach maturity size at an estimated weight of 18 kilos, and the males even sooner than that. Now, the spawning profile of our broodstock. So the spawns, as I mentioned, occur naturally, and the temperature is the physical factor that has the most control over spawning. Studying the monthly averages of our spawning since 1996, we see a pattern that usually the spawning decrease or even stop during the months that correspond to the upwelling season in the Panama coast. That is when the average temperature drastically dropped from 28 to 24 degrees Celsius. The minimum temperatures can reach even lower than that. After we have the peak of our spawning season in the months after this drop, when the temperatures are reaching back up. And after the rest of the year, we have a fairly constant spawning and constant temperatures at the high 28s. We relate that also with pH, even though we don't have so much differences in pH, variation in pH, because we have a closed system that we control well. And salinity. And here you can see that the salinity, the peak of spawning season, corresponds to the beginning of rainy season in this part of Panama. So when the temperatures, when the salinity starts to drop as well. So 51% of our spawn occur at mean temperatures of 25.7 to 28.4 degrees Celsius and salinity of 31 to 34. And our annual average for eggs collected was 67 million eggs. And this is the average standardized egg production per year. It's standardized egg production because we're talking about the total number of eggs collected related with the spawning female biomass present in the tank during the same period. And we can see that our egg production has decreased over time. So we are starting to analyze this in depth to see what we can do about it, what is going on. But overall, the frequency of spawning at Ashotinis has been very constant. In fact, in 80% of the time, the fish were spawning at the lab. This is the frequency of spawning events in each month since 1996. And we still can count on our hands the periods in which the fish stop spawning for more than 3 months in a row. But also we can see that this has become more frequently in the past years. Now, with all this analysis, we can look back and understand what made the fish stop spawning. Sometimes was a problem of sex ratio. There was not enough females or males during certain period. Sometimes a longer upwelling season. Sometimes we still cannot explain why the fish stopped spawning. We call that the Ashotinis factor. And we now are witnessing at first hand the effects of climate change in our own broodstock tank. 2023 has been a record-breaker year for high temperatures ever recorded. And we are going to start studying the effects of this long-term exposure in our fish. So looking back in time, all this broodstock management program allow us to conduct different collaborative research with many institutions all over the world, many of you who are here today. And we look forward to keep working together. Also, we were able to translate our experimental research into many different scientific publications. You can access that all in the IATTC website. And looking forward, our group is very focused now on the studying with juveniles. So far, we have been very successful studying the early larval stages. And in fact, you can check our updated research with the presentation that my boss, Dan Margulis, will throw tomorrow in the larval culture section. So now we're focusing to the juvenile stages. We also want to close the life cycle in captivity. And we have a lot of interest in research topics that can be applied directly to aquaculture. So our research will continue to support the aquaculture development of the Yellowfin Tuna. And that's all. Thank you. Did I calculate? There's no time for questions. Did I calculate correctly the time?
No.
No.